Okay, folks, this is a second video in domains, and specifically I want to look at domains of radical functions. So last time we said that, say, for a function like this, f of x is equal to the square root of x, this is defined for x greater than or equal to 0. That is, it's the domain would be the set of x such that x could be any real number, and x is greater than or equal to 0. That's the domain in what we call set builder notation. Or we could go ahead and give the domain in interval notation, and you need to be comfortable with looking at it or giving it in either way. So this is what we call interval notation. So this is interval notation. Let's just do a quick recap of a couple of properties of roots. So for example, if I looked at this, the nth root of a, we call the expression a inside the root symbol, this is called the radicand. And we call this symbol right here the index. Of course, if no index is given, like it is in here, the index is understood to be a 2. Okay. So let's go ahead and find some domains of some more radical functions. Well, let's just say I give you f of x is equal to the cube root of x minus 7. Well, what numbers am I allowed to plug into this function? Well, this might be a bit surprising, but the domain of this function, the domain of f, is the set of x such that x can be any real number. How come? Because what's the index of this radical? The index of this radical is odd, or it's an odd number, it's 3 in this case, but it's an odd number, and we can take the nth roots of any expression provided that n is an odd number. Okay. Let's look at then let's look at some even indexed radicals. Well, let's say f of x is equal to, let's say, the 8th root of 3 minus x. Okay. Well, because the index here is even, I can only take the 8th root of values that are 0 or greater. So I need to set the radicand, that's this expression right here, not just the x, the entire expression. We need to set the radicand to be greater than or equal to 0. So let's go ahead and do so. We need 3 minus x to be greater than or equal to 0. That tells us that minus x must be greater than or equal to negative 3. I subtracted 3 over. Or if I divide both sides by a negative 1, then I get x must be less than or equal to 3. Recall the property in algebra that says when you divide by when you divide an inequality by a negative sign, you have to reverse the direction of the inequality. So now we can go ahead and give the domain of this function f here in set builder notation. Would be the set of x such that x could be any real number and x is less than or equal to 3. Or if we wanted to give the domain in interval notation, it would go from minus infinity to 3. And we go ahead and put a bracket there. Okay. So don't be alarmed here. There is nothing that says I can't plug, for instance, negative 1 into this function. If I asked you, what is f of negative 1? Well, negative 1 is inside the domain, so this better be defined. And sure enough, we see that it is, because this would ask us for the 8th root of 3 minus a negative 1, which is equal to the 8th root of 4, and we can go ahead and compute that. It's not a nice number, but we could go ahead and compute that. So let's keep going. Let's look at one that's a little more challenging now. Let's say I give you this function here, g of x is equal to 1 over the square root of x minus 2. Okay. Well, what do we need to do now? We need to set the radicand to be, normally we would set it to be what? Greater than or equal to 0. But in this case, I don't want the output of this square root sign to be 0. So even though for taking the square root, it's okay to let x be, for instance, 2, because that will then be divided into 1, I need to make sure I'm not dividing by 0. So in fact, we need the inequality to be a strict inequality, strictly greater than 0. So this gives us that x must be greater than 2. So the domain of this function g is a set of x such that x can be any real number and x is greater than 2. Or if you like, in interval notation, it would go from 2 to infinity. So let's go ahead and combine that with another problem here. Let's look at h of x is equal to x, let's see, the square root of x minus 3 all over x minus 5. Okay? So this is a combination problem. In this case, I have two problematic operations. I'm doing division, and I've got a square root. So for the square root, we need the radicand to be greater than 0. So we need x minus 3, the radicand to be greater than or equal to 0. So we need x minus 3 to be greater than or equal to 0, so we need x to be greater than or equal to 3. But for division, we need to make sure the denominator isn't 0. Which means we need to make sure that x minus 5 does not equal 0, which means to make sure that x does not equal 5. So let's put these two ideas together then. Putting them together, we see that the domain of h will be, let's go ahead and just do it in interval notation. In interval notation, it will go from 3 up to 5. And I get to include 3. How come? Because of this greater than or equal to. So if I plug in a 3 here, that gives me 3 minus 3 in the numerator, which is 0, and the square root of 0 is defined. And then 3 minus 5 in the denominator, which is no problem. I can do that. So I can plug a 3 into this function, but I cannot plug a 5 in, unioned with 5 to infinity. That's the domain of this function here. I hope this is helpful.